Alright, let's look at some Sage code to solve the y double prime plus y equals 0. And so what I did was I have x, I'm going to do y of x, so x is the independent variable, and we're going to need that for how many coefficients I want to do. And so I just start out declaring here the symbolic variables. Now I have to do this thing a definition, and the way I do a definition is I say def and then the name of my function that I'm defining and whether or not it has any input in it. If you're growling in the back, that's just my stomach. Actually, it's my two puppies. But so here's the definition, and I just start with my polynomial that I'm going to make. I make it 0. Now here are all my coefficients that I could have. I could go from A0 all the way to A10, and I could add more. I could have A11, 12, 13, you know, and so forth. But I do this much. If I do add more, I have to add them here. I have to add them to the end of this, so those are both the same thing, and then I have to add them here. So what I have is that I've made these new symbolic variables called A0 through A10, and then I make an array here, a vector of them A0 through A10. And now I make my polynomial, and I simply do it by going through going through I up to, you know, from 0 up to just 1 under whatever this range says. So notice this, you know, I could go up to n. This says n plus 1, so I can actually hit that n there. But all it's doing is it's taking this, you know, so it'll take a of 0, which is a0, times x to the 0. Then it'll take a of 1, which is a1, times x to the 1, and so forth up to a10, x to the 10, for up to 10. But I could stop it at 5, and that's what I do right here. I say y equals y of 5. So I make my polynomial. Here I take its first derivative, and here I take its second derivative. And these are just polynomials. The first, you know, they're truncated power series. And so that's what I have to do. I can't. I looked at trying to use the sum formula and so forth that they have in Sage, but it doesn't work well with this a of I thing here. So this is what I did. It seems to work pretty well. So I've got a bunch of stuff commented out, but here, you know, I make the function and look at its first and second derivative. So here I evaluate, and if we look down here, there they are. You know, so I have, you know, a0, a1x, a2x squared, a3. Yeah, that's the one puppy trying to get the other puppy to do something. And then, you know, here's the first derivative, right? And bring down the 5 and so forth. And then the second derivative, bring down to 4. 4 times 5 is 20, and that leaves a 3. And so there they are. Okay, so that's what I have so far. Then I define my differential equation, and remember we had y double prime plus y. So here I take my ypp, y double prime, plus y is my differential equation, and my initial conditions, I had a y0 was 0 and a y prime of 0 was 1. So I put those in, and then I create my equation 0, but notice the equation 0 is actually, I'm not taking a derivative here. I substitute in, right? I have my y double prime plus y. If I had anything on the, you know, so remember the right hand side of that was 0. If I had anything on the right hand side, I'd subtract it, put it on this left hand side, and just not have it equal 0. And the reason it just, I think, makes my life easier. I'll just always have equals 0 here if I start my differential equation out the right way here. Now, so here, what I do is I say, I want my differential equation, I want to collect the x, and I want to just look at the 0th coefficient. Okay, so let me get rid of that just so you see what we would have. So Control X to get rid of it. I evaluate, and notice what I have. I have this thing, and see there's some constant terms there, the x terms, x squared terms. So it's nice it ordered it well, but it'd be nicer if it collected the terms. And so going back to this, that's where I collect the terms. And so if I get rid of this coefficient part, they're playing, and I evaluate. Notice it collects the terms, so here's everything times the x cubed and then x squared and so forth. So I can collect the terms, but remember what we really want to do is just start solving for our coefficients, starting with this, this part down here. Solve for a2 in terms of a0, and then we'll solve for a3 in terms of a1, and so forth, and ladder up. We let j start at 0 and go to 1, and then 2 here, and 3, and we look at those coefficients. And so what I do is, if I add in the coefficient part, so if I say, oh, take the coefficients on x and take the 0th coefficient, then that's the constant term. And so now when I evaluate that, I get that equation that I wanted. So there's the a0 plus 2a2 equals 0, like we had when we did it by hand in the video. And then what I want to do is solve for a2. So that's this next part, is I'm going to use an uppercase a2 and take that equation, substitute in my a0. That's part of the reason I printed it out. I needed to know what I needed to sub in. So I substituted in my a0 equals y0, and then I solve for a2. Now the 0 in square brackets in the right hand side, again, we can show you what that's doing. So if I take that away, evaluate, then what we see is we get a2 equals 0 in these square brackets. Well, you need to get to that 0. I want to get to that 0. And so that's what the square brackets around the 0 do, is it says, okay, I've got a list down here. This is a list. Well, it's a very short list. It's a list of length 1, and I want that first term. But again, lists start with the 0 term and then go from there. So I want the 0th term, which is the first term. And so if I hit evaluate on that, notice it got rid of the square brackets. Well, now I just want the 0, so I just want that right hand side of that equation, and so that's what the dot right hand side does. And I evaluate that, and there's just the 0. So I know a2 equals 0. So then I just copy those 4 lines. So what I did was I took those 4 lines, I copied and pasted them, and then I changed the 0 to a 1 for equation 1, and the 0 here I changed to a 1 because I want the x coefficient. And so I do that, and so there's my 0. Now here's my second equation, a1 plus 6a3 equals 0. And now I also did the A3. So what I did was I copied actually 2 lines at a time. I copied those 2 lines, fixed them up with the ones, then I looked at it, then I copied those 2 lines and fixed them up with A3 instead of A2, and again I needed equation 1. Back here it was equation 0, and here I needed A1. Again, I see I need to solve for A3 in terms of A1, so I needed to sub in A1 into that, but A1 was y prime 0, and again I solve for A3, and the 0 right hand side stuff will always do, and then I show my A3. And just like we had before when I did it by hand, we get minus 1/6 for A3, and then I did the same thing again. Now the reason I'm using I started with equation 0, it's because it was x to the 0, and then equation 1 because it was x to the first, equation 2 x to the second, so I want the x squared term is what that's saying. Now I'm just going to undo all 4 of those, but again I did 2 at a time, evaluate. And when I got down here, I saw that I wanted to solve for x4 in terms of x2, and so and again, well, when we do that we get 0 because, well, x2 was 0, so x4 is going to be 0. We saw that all the even terms were 0, and but I solved A2. Little a2 is equal to big A2. Okay, I'd already found big A2 up here, and that's why I needed to get just the right hand side, that 0, and I put it in and I get 0 again. And now I do equation 3, show equation 3, I get to A5. Now an A5 is the last one I can do because I said back here I only wanted to go to 5, and so that's all I have. And so I show A5, and we get down here, and A5 was 1 over 120, which is what we got before, and so again this was we know the answer is sine, and we had A1 was 1, A3 was minus 1 over 3 factorial, and A5 was positive 1 over 5 factorial, and that's 120. And so we are getting the same answer we got before, and it is the sine of x if you look at that Taylor series, about 0. And so this is the code. I'm saving this code and putting it on Blackboard for this particular example. Again, if I have a different differential equation, I'll have to sub in different things. So for instance, we had a y double prime. I don't remember exactly what it was, but it was, I think it was something like an x, like a minus x squared times y prime plus y, and then we had equals x cubed, I think, and so I would need to do minus x cubed like that, and then that's all equal to 0. So I could put that differential equation in, start this whole process over. I would have to start back here at equation 0. All of this stuff would be wrong, most likely. I don't know that for a fact, but most likely it would. But let's just see. So I'm going to get rid of all that and evaluate and just see what we have. So here it looks at the different items, and then the first equation, and interesting, if I had that right, if I have this right, I had forgotten that it was just A0 plus 2A2. So actually the first A2 will work fine, and possibly even the A3 works okay. I can try it. I'll just get rid of the stuff below that. Evaluate. Yeah, And oh yeah, it's coming back to me. You know, we had the minus 1/6, but now it maybe starts to be different. I will do, you know, so we get to equation 2 and the squared component. Looking at the original differential equation up here and the squared component, where are we? There we are. There's the differential equation. When we get to the y squared stuff, we've got the YPP, but I think we'll also have well, that's cubed, and that might start, well, no, because yeah, I think with the squared it started being different, maybe. And so if I look here at equation 2 and just get rid of that for a minute and evaluate, we'll see if all I need is, yeah, see, I'll have to substitute for both A1 and A2 to get A4. So if I put this stuff back, to get A4, I need to substitute A1 equals, and that wasn't an uppercase A1, I could have made it that, but it's a Y prime 0, YP0, comma. I think that works. And then I'll do the show A4. And we get 1/12. And I don't remember for sure, but that sounds right. 1/3 times 4. Yeah, that does sound right because it was 2/4 factorial. So, you know, we get that same number 1/12. But you see, I had to substitute for both of those up here, so I just did it with a comma in the substitute. I just said substitute A1 was that, and then A2 was this A2. And if I needed a A3, I would have put that in as well because we have A3 up there. So that's the idea, and you just repeat those that way to do these steps, but it is the same steps again. We substitute in for the equation, we collect like terms and look at the coefficients and just start moving up through our powers of x. And so it is exactly the same steps. I'm just getting Sage to do the algebra for me. Okay, so we'll call that good for this one.